Hello, in these videos we are going to find the inverse Laplace transform, and our method is to use tables. And I have a table above that I made by typing LaTeX, and but I keep actually expanding this table. It's getting bigger and bigger. I do work out a problem, and then I think, well, why don't I just put that in the table rather than using properties to derive the formula? So you can just make the table even bigger and bigger. You might take a screenshot. I mean it's so small here that's probably impractical, but you can do a web search of Laplace transform table, and then look under the pictures. It'll bring something up. So all right. So one of the things I'm just going to tell you that's on the table is that. So here's our table. If I have f of t over on one side, well, okay, and then say this is f of t. This is how the table's set up on the tables. And then here's the Laplace transform f of s. Okay, so all right, so one of the things that we have is that you have t to the n. The Laplace transform is n factorial s to the n plus 1. Alrighty, so you see how this is working over here? We have on the left the function, and the right we have the Laplace transform of the function. But also what happens is if we multiply by e to the at of any function, then we can copy down that same result for the Laplace transform, but we replace s by s minus a. All right. Personally, I have just tiny bits, I looked this up, just double check, but I think I know this. It's at, and then we have s minus a. Okay. So under this, problem, what I can do is I can work on this a bit, and well, I see that this is s minus 1 to the 3 plus 1 power, clearly 3 plus 1, and then I look at 3 factorial. 3 factorial is 3 times 2 times 1. Okay, that conveniently is sitting right here, which is 6. But, okay. In general, if it's not there, I don't know if it's easy to understand, but if suppose hypothetically, instead of having 6 there, say I had, hypothetically, suppose I have 7, then what you can do is you can bring the 7 outside and you multiply by 3 factorial, and then you divide by 3 factorial. So that's how you can, get the 3 factorial up there. You put the 3 factorial up there, and then you just divide by it, because, it's like multiplying by 1. Okay, but this problem's a little bit easier, but maybe in a way sort of too easy for us to get our general sense. So f of t is our inverse Laplace transform, and we're just going to denote it as that. And it's going to be, actually, according to our table, it's e to the 1 times t, so a is 1, t and n is 3. Okay, and now I'm abbreviating this table, and so maybe that's not as good, but I'm not pointing out or saying in here that, in fact, for this to work, s has to be greater than a, n is an integer. There's little things like that. And also, one of the things I really should write, though, is that the general formula is e to the at ft. That transforms to capital F s minus a. So you take the Laplace transform of f of t, and then you replace s by s minus a. I said just do that, but everything can be, it requires some concentration. Okay, now moving on to this next one, what I see is that the denominator does not factor. It's an irreducible quadratic. It means it doesn't factor over the real numbers. It can factor over the complex numbers, but let's not do that. And so what I have is g of s equals 2 s squared plus 2 squared. Another formula that we have is that Sine bt has Laplace transform of b s squared plus b squared. And so in this case, b is equal to 2. So our inverse Laplace transform is sine of 2t. I'm not sure, I sort of was going into this sort of thinking that I didn't really quite remind everybody what the inverse Laplace transform is you're starting in this column. You have a Laplace transform of the function. So you have a Laplace transform, and now you're going back to find what function gave this. What function is when I apply Laplace transform? What function when I apply Laplace transform gives me this? Wow, that's sort of getting stuck for sure on those words there. So you can check it out. Apply Laplace transform e to the t to the third power, and you'll get this. One hopes. Okay. Now, for this next one, I'm going to use a formula which is all right. I have another formula. Cosine bt is s over s squared plus b squared. That's the Laplace transform. Now, we do have an irreducible quadratic. You can try the quadratic formula. It does not factor. If I use the quadratic formula, underneath the radical is b squared minus 4ac, also known as the discriminant. The discriminant is going to be negative, so that tells us if we use the quadratic formula, we get square root of a negative number, which means it does not have real roots. So it's irreducible. Now, let's now do another thing that we need to do, a technique, which is when we have a irreducible quadratic, we complete the square, and with the idea that this is going to give us something like s squared plus b squared. It's going to be something squared plus something squared. Let's see what happens. Okay, so h of s is equal to s plus 1, and then in the denominator I have s squared plus 2s. The rule of completing the squares, I take the coefficient of s, divide by 2 and square it, so that gives plus 1. So now I have 1. You can take the 1 away from the 10. 10 minus 1 is 9. So I don't know if I'm borrowing because I'm not going to give it back, but I take 1 away from 10, you get 9. So why would I do that? Because now I have s plus 1 in the numerator, s plus 1 squared plus 3 squared. All right, that looks a bit like this formula, except s has been replaced by s plus 1. But that corresponds to taking this formula cosine bt and multiply by e to the at. So yet another formula that we can use. All right, so apparently the Laplace inverse now, we're all set up to go. A is equal to, that's a little tricky, but a is equal to -1 and b is equal to 3. That's right. I mean, it's like doing all this pretty good math, and then I'm getting mixed up with the tiny little thing of that over there, getting the negatives and positives. So it's going to be e to the negative t cosine 3t. All right. All right, so here we go. Yet another formula, except I'm sort of not ruining, but just sort of running out of room on my table. So I'll just, I don't know, continue like this on the table as if it was uninterrupted. As if it was, but it was interrupted. Okay, so look, for this this can be expressed as e to the negative 3s times 1 over s squared. Well, the 1 over s squared, that falls into the category of n factorial over s to the n plus 1. Let's even put that over here on a table, my resume table. If I have 1 over s squared, that corresponds to t. Because, see, this is n equals 1. So it's 1 factorial s to the 1 plus 1 makes 1 over s squared. Now, we have yet one more thing, is if you have e to the negative as times f of s as the result of your Laplace transform. This corresponds to the unit step function uat times f of t minus a. So the unit step function is 0 up to a, and then 1 after a. So what that does is that it makes that this f of t is multiplied by 0 before a and then 1 after a. So it's like it's turned off. It's 0 all the way up to a, and then it's equal f of t minus a after that. And it's not super happy about squishing this in here, but okay. So in our situation, if I have e to the negative as times 1 over s squared, that's going to correspond to eat. 1 over s squared corresponds to t, so that's going to be t minus a. Let me put a dot because it's not, okay, that's what it's meant here. And I put that in the table. So in this case then, a is 3. So f of t is equal to u3t times t minus 3 to the 1 power. Well, this is challenging, good for the brain. And just do this and you'll hopefully stay young, keep your brain sharp. Okay, so I feel like maybe it would help if I just put a little box around this part that's the table. Maybe it would organize the page a little bit, but besides that, I don't see what I can do, except, maybe someone else could do better, but this is all I can do, I think. But maybe I'll come back and make a new video, improve upon this one. All right, well, do you see this picture right here? This is copied and redone by myself. Those are oranges. Those are not tomatoes. And those are mountains in the back, Saddleback Mountains, Orange Coast College. Okay. Take care. Be safe.